Let's talk about airtightness now. As Naya said, my name is Lüder Herms. I'm from clima, Germany, working at clima since 11 years now, and I take care about our export markets, and I'm active in the research and development department. From my education, I'm timber framer and civil engineer, so I know the building timber constructions from both sides. So I've learned it. I've worked 5 years as a carpenter, and then I decided later to study, and I've realized tons of airtightness systems in this year 2000 to around 2012. Proclima is a producer and developer of building systems for achieving the building tightness in timber constructions. We are mainly known or very active with these intelligent vapor barriers, which we install on the inside of insulated constructions. The speciality of these membranes is that they are diffusion tight in winter. They do not let moisture enter into construction, but in summer they can change their molecular structure, become open to diffusion. So moisture which enters the construction unforeseen can dry out to the inside. We keep by this dry construction, mold-free construction, and create with this very nice envelopes for the people who are living in the buildings. Of course, we need to achieve airtightness. We need different sealing materials. We have tapes, we have glue and cartridges, we have grommet solutions, and different systems. And the third big part of our activities is the exterior sealing. We are working there with breathable membranes, which offers to the construction an active diffusion transport of moisture from the inside to the outside. Yeah, with the systems we are not only active in Europe and in Germany, but nowadays we are active worldwide in more than 40 countries. Yeah, we're mainly in Europe, in Russia, in Turkey, Greek. We are building now passive houses in Chile and Brazil, and Mexico is now a big passive house movement. They built their 600 passive units for social housing, supported by the European Union, to bring this knowledge transfer. But we are as well in Australia, New Zealand, Taiwan, Japan, South Korea. So yeah, we are worldwide active in all these climates where you have the difference between a cold winter and a warm summer. So this is the area where you need to work with airtightness and diffusion systems. Our approach is not to build in every country our own subsidy. We are working with partners, and so we're working in Ireland and UK, I guess since 15 years together with Ecological building systems, to have these people who come from the country, who knows how the constructions are realized, who know how people are thinking, and this is the key to our success. And yeah, we're very happy and delighted to be invited here today. Good. Our slogan is Proclima, and the installation is perfect. And before I start about how to do CLT airtightness, I want to show you a little bit about the basics, why we have to do airtight, just in a few frank words. And to understand why the installation is perfect with Proclima, it makes sense to take a closer look how an insulation material is working. And an insulation material exists of the material itself, wood fiber, cellulose, mineral wool, stone wool, whatever, and a lot of air, which is found within this insulating material. It's the same principle you know from a wool pullover. So when you wear this pullover in wintertime, it keeps you warm and comfortable as long as you are in a numb, windy area. Because if the wind can blow through the pullover, through the wool, it transports the warm air away, and you start at once to freeze. What do? You take a very thin windbreaker. The windbreaker avoids that the air can stream through the pullover, and the heating effect of the pullover started as once. And this is the same principle we found on the construction site with fibrous insulation material. Only an insulation material which is protected against air movements can insulate 100%. Good. This was measured by the Fraunhofer Institute in the year 1989. They took 1 square meter of wall and installed it between 2 climate chambers. They created on one side in this climate chamber a winter temperature of -10 degrees, and on the inside a temperature of +20 degrees. It was 14 centimeters mineral wool covered on the inside with a, how do you call it, PE sheet? Vapor control layer, VC. VCL, absolutely airtight. And then the engineers calculate and measured how much energy do I need to keep this temperature difference stabil. And they were very happy because theory and practical worked very well together. They found out the measured and the calculated U value was 0.3 watt per square meter Kelvin. But then they wanted to know what happens if we have a small leakage inside. So they entered a gap of 1 millimeter width and 1 meter length, and they measured again, and they found out that the U value reduced to a factor of 1.44. This means we need 5 times more energy to keep this temperature difference stable, only by the small gap of 1 millimeter. Yeah, this is not nice, because we need more money for heating and cooling this building, but it's not so dangerous. More dangerous is moisture entry. And so during the same research, they made a measurement how much moisture is transported in the construction. And first they tried it with a perfect airtightness layer, and this VCL, vapor control layer, has an MVTR value of 150 meganewton second gram. So it was a very tight material, and they calculated how high is the diffusion transport, and they measured the moisture transport in the construction, and they found out within 1 day and 1 square meter of wall, half a gram of water is transported in the construction. It's good, not dangerous. But what do you think happened when they make the same measurement with this gap of 1 millimeter width and 1 meter length? This means 1,000th still of the surface was not airtight. How much moisture do they found inside? An idea? 5 times more?
6 liters.
6 liters, unfortunately not. It would be more shocking.
Half liter, 100 times.
They found out it was 800 grams. So 1,000 times more moisture than calculated was transported in the construction only by this warm air which is penetrating in, condensating, and transport water inside. But when we see these figures, most of people say, yeah, come on, we build houses with insulation since 20, 25 years and they are not airtight. They all must be rotten now, but they are still existing. Why? Because we have another building performance nowadays. So the protection against moisture entry becomes more and more important in modern construction. And this is a picture which shows us very, very clearly what happens. So we insulate our houses better from the outside. And by this we create lower surface temperatures on the outside. This is a non-insulated building, and this part was insulated. And the lower the surface temperature on the outside gets, the higher the condensation risk is. And if we have condensation in the construction, it stays longer inside if the surface temperature is colder. So here we heat it faster away, and here the moisture stays even longer and has time to create a building damage. And then we have a second impact, and this is the way how we have these air leakages in these buildings. All buildings have been absolutely unairtight. So the warm air was streaming in short streaming waves very fast from the inside to the outside. These leakages are very small streaming waves, so the warm air streams very fast from the inside to the outside. Modern constructions are more airtight. This means when we have an entry on the inside, the air may take a longer streaming way to the outside, and by this longer streaming way we have longer time that the air can cool down, and that we found condensation. And this is what we found more in modern construction. We're trying to build as airtight as possible. We try to build as windtight as possible on the outside, and the air which is streaming through the construction needs a longer time. All these problems we have solved with the so-called timber frame constructions. We are working with timber frames constructions since years. There are hundreds, thousands or millions of buildings realized, and we know what to do. We have this building physics, we can control it, and it's working very fine. And now we bring the timber constructions to a new level. We try to gain more possibilities to build houses instead of using concrete and steel with these CLT elements. And the CLT elements have been used in a couple of buildings, or a lot of buildings as well. And we know that they will pass the blower door test, that they offer a certain airtightness. They are quite good. And when you take a look at this, you see, okay, it looks a little bit like massive wood. And what I would take today a look at the building physical properties. And the first is the diffusion resistance. Is the CLT element diffusion tight enough to protect the insulation against moisture entry? This can be easily calculated with the formula. So as D value, I will transfer it later to MVTR. It's calculated with the mu value multiplied by the thickness of the material. And if we take the diffusion resistance value of CLT, it's between 40 and 80. 40 is timber, and it might be a little bit higher due to the glue we bring in between the layers. The thickness in this example is 9.6 centimeters. For this formula we need it in meter, 0.096 meter. And when we put it now in this formula, we have the SD value, 40 multiplied by 0.096 meter is an SD value of approximately 4 meter, and this is clearly enough when we have on the outside a diffusion open material made with plaster above it. SD transferred to NVTR multiplied by 5.1 with an NVTR value of approximately 20, so we can use it as a vapor barrier as we want, so CLT can do it. When we take a look at these components, they look really airtight. So they look like a massive block comparable to concrete or whatever. And nowadays we have a lot of CLT producers in the market. So, and they're coming more and more. And every CLT producer is using different wood, different machines of producing the CLT, and they say different things about airtightness. Some say we need 5 layers of timber to be airtight. Some say we need 3 layers to be airtight when we have on the inside this high quality visible surface later, and. So what is important when you plan to build with CLT, ask them if they have tested their elements about airtightness. So they can send it to an institute, they build it in a chamber, and then they measure how much air can stream through the element, and then you know how good the quality is. Is it a good airtight material or not? So then you have the first idea what happens. And I would ask for this during the planning process if I want to use the CLT elements as a diffusion retarding and airtight. There are 2 main ways of producing the CLT. And the first way is that we have only glue in between the layers, but the narrow sides of these single boards, there's no glue in. So this is the lower quality. And then we have the higher quality with glue between the narrow sides of the different timber elements. And of course, this offers clearly higher airtightness than elements without the side bonding. This is a question you can ask to the producer as well. How is your element produced? And when we see pictures of CLT, they always look like this. So very nice material without any gaps between the different layers. But I've brought you some pictures from building sites, and then it looks differently. So here you see we have gaps between the different layers. They cut here some, this is new, they cut here some expanding gaps in it because the wood is drilling and shrinking, and come to this point later. And we found even cracks within the timber. So something is happening in these elements when it's installed. And the reason for it is the dwelling and shrinking of timber. So we expect the wood to be installed in a very safe way on the inside. So we have always same temperatures between 20 and 25 degrees. But we found on the inside, due to the climate situation in winter and summer, different air humidities. So in summer, it can be between 65 and 75% air humidity on the inside, and then we have the moisture content of the timber at 20 or 25 degrees, between 14 and 11%. In winter, it's even drier, the air on the inside, so we are between 55 and 45% depends on how we use this building, and there we have the moisture content between 8 and 9%. So we found between winter and summer a change of the moisture content in the most extreme case of 5%. And the funny thing is that the dwelling and shrinking is happening exactly in this moisture level. So when we have a very low moisture content and the timber is getting more humid, the first moisture is transported in the cell walls of the timber, and the cell walls are expanding and shrinking. And this happens at the CLT elements as well. So you can calculate it in the radial direction of the timber. We have, by a timber moisture change of 1%, a changement of the dimension of 0.3% average. The thickness of each CLT board is approximately 1.10. Differ, of course, but in this example I take it. And the timber moisture difference between winter and summer is 5% when we take a very negative example. And the dimension change is 0.1 meter by 5% by 0.003 percentage of the length. This means we have between winter and summer in each board a dwelling and shrinking of approximately 1 or 1.5 millimeter. And the funny thing is that the element itself, it's very stable. Why it is? Because it's glue with the elements which are in the longitudinal direction, and so it's avoiding that the whole element has big movements, but we have the tension in the moisture, in the timber. And due to the tension, it can come to these cracks we can see after installing. And this is a nice example. So we built this model. It was for an exhibition, a table model, and when we built it, it had no cracks. But after 3 years standing in our office, we have found really cracking in the surface of the timber. When we have a visible side on the CLT visible on the inside, we have to drill in these holes for the plugs and for the mill slots. And of course then we have, instead of 3 layers or 5 layers of the CLT element, only 1 or 2. So all these effects have an influence on the airtightness. Not a big one, but there is one. This was measured by the SINTEF in a couple of years ago. The SINTEF is a Norwegian building institute comparable to the BBA. So they are just checking if a component and if a new way of building houses is working or not. And they have taken CLT elements and then they measured them. I have to say, here they didn't seal the overlaps from the outside with the tack, that they just nailed some timber above it. So it's a very untight building, but they found out what I explained now. So when we have the narrow side not glued, we have a clearly higher airstream through the component instead of the boards which are glued at the narrow side. And then they found out the moisture the timber is, the airtight the CLT element gets. So when we have 40%, so a summer condition, they are clearly airtight instead of winter when we have this lower moist condition. And this shows clearly what I explained in the beginning. We have some effects on the airtightness of CLT elements. And what they found out is, when you want to be sure that you're really airtight, install a membrane from the outside, then we have a good weather protection and we have really 100% security that this component in construction is airtight. But I have to say, research is a couple of years old. The quality of the element production is rising since this time, but they show clearly what happens to the timber. Good. Now to talking about how to make the CLT airtight. And there are 3 different possible ways in the market. So the first way is we put some expandable foam tapes in between the elements, induced by the weight of the elements. We press it together and it should be airtight. The second one is to seal the overlaps from one side. It's best to do it from the outside with an airtightness tape. And the third possibility is to wrap it all and to divide the static questions from the airtightness questions to work with an additional airtightness membrane. And I want to talk about all of these 3 possibilities to see where are the advantages and disadvantages. And I want to start with this possibility to put the sealants within the element connections. And this is used approximately in 10 to 15% of all buildings in Germany. So I made a research talk to a couple of carpenters. And why? Because when you install these heavy elements and you bring it to the ceiling, and you have here installed the airtightness tape around, and it does a little bit like this, and you have to bring it in position later, it happens very easy that you destroy these tapes, and so people don't like to work with it, and the result is not so easy to achieve. And then we have another effect. If we have here the tightening layer through these gaps and non-sealed narrow sides, we always found an air streaming from the inside to the outside. So this is working, offers a good airtightness, but not a very good one. So, and another thing is very important as well. So if we work with thick tapes and we put the elements above it, and we have 3 centimeters in the bottom and 3 centimeters in the top, we have to respect this by planning the elements dimensions. So it must be 6 millimeters smaller. It's not so easy. Yeah, so application problems, they're clear. The tape can be get out of place during the application of the heavy elements. And for architects, I've seen a lot of architects are here, it's you're responsible for the quality, and it's not possible for you to go out to the building sites and make a visual control if it is really airtight, if they have installed in every little gap a tape. And it's very expensive and difficult, nearly impossible to repair it if you found later leakages, because you cannot lift the house again and repair it. So it's impossible and gives leakages through cracks. The most common way of making CLT airtightness is just sealing it with thin airtightness tape. So it's working very well. We've done it in a couple of thousands of houses, and it's good. So we have on the inside no visible gaps because the CLT can stand directly on the CLT. We don't have to adopt the element dimensions. The tapes can be easily installed from the outside. It's easy to control for architects. You can see if there is a blue tape stick around or not. And if they forgot maybe a couple of meters, we can add it later without any problems. One problem we have is these cracks we found in the building. So here we have a crack, here is an unbonded narrow side. And if we install now just the tape sticked straight over it or sticked like an L to the concrete, we create this streaming waves behind this tape. So this was so a producer of CLT came to us and says, come on, we have this problem, we do not know when the cracks occur. We know they are coming, but we cannot say how many are coming and when they are coming, if they're coming later. We need a solution to seal it. And the only solution to seal it is when we make a tape connection first to the first horizontal layer, and then we close these gaps. And to do it within one tape, we developed a very simple solution. It's a tape where you have 3 possibilities of bonding it to the CLT. So you stick it with one part above the CLT, and then you have the second part you stick to the first horizontal layer, so all these gaps are closed. And then you have another layer which you can stick to the other element or to the concrete slab. For the installation, it's better when you just fix it with the tape to the CLT element. Otherwise, the CLT element is standing on the tape, and then you have one thing. Yeah, you bring out the CLT element in place, and then you can simply realize the airtight connections to the floor. When you want to use the common airtightness tapes, make sure that you overstick it from one longitude to avoid the streaming cracks through it. So you have always close these streaming gaps. And when we talk about tapes, this is interesting because there are so many tapes available on the market. They are green, yellow, blue, purple, whatever. And when you make the test of an airtightness tape, what are you doing, or what are the installers doing normally? Taking a piece of tape, putting the finger in, and then it's sticky or it's not sticky. But this does not really says anything about the quality of the tape. And I'd like to bring you a little bit closer why we've chosen for clima a special glue quality. We are working with the so-called solid acrylic. It's 100% acrylic, and we have this main tape. Our most successful tape is the Tescambana for inside-outside use, with very resistant spun bond barrier and a water resistance glue. And water resistance is one of the main differences you found on the side between these different glue qualities. So when you take a common acrylic dispersion glue, this is another way of production. These glues can react with water because the glue is produced out of the dispersion. It was solved in water before it was brought to the material, and it was dried to become only acrylic. And when these glues get again in contact with water, they get soapy. So they put some water in their structure again, they re-emulgate, and then they lose their adhesive strength. This picture is made on I stick these different tapes on a substance membrane, put it 24 hours underwater, and tested the next day how good is the adhesion. And our solid glue is produced without water, so we have no reaction with water when it gets later again in contact with it, and by it does not lose its adhesive strength even if you put it underwater. So clima tapes are absolutely watertight. The second thing which is important to know about tapes is how a tape is working. And when we take a closer look about the forces we have in the tape connection, then we have 2 main influences. We have adhesion. This means how good is the glue sticking to a surface. And then we have cohesion. And cohesion means how strong, how high is the inner strength of the glue itself. You can compare it very easily with two materials you know very well. So this is a very fluid honey. You know it when you put a spoon in this honey and you turn the spoon around. So the honey is dropping down and only a thin layer of honey resists at the spoon and it's absolutely sticky. But it has such a low cohesion that it cannot even carry its own weight of the honey so that it's transferable. And the other extreme is hard concrete. Hard concrete is sticking to nothing, but you cannot move it apart. This is a very cohesive material. And we have now to combine everything on a tape. A lot of tapes are produced to convince the installer on the building sites. They said, okay, how is the installer testing it? Putting the thumb in it, and if it's sticking well, they are saying it's a good tape, and if it's not sticking so well, they say it's a bad tape. But the funny thing is, the more softer the glue is, the higher is the impression that you have a very good quality tape. So it sticks very good on your thumb. It's penetrating fast in the surface of your fingerprint, and this is why I think it's good. But then on the building side, this can happen. So this is a very sticky tape. They sealed an overlap, and we have here small tensions on it from the insulation, and due to its softness of the glue, it's swimming like honey. And you see this connection will collapse in a couple of short time. We made a research, so we put 56 tapes in our basement, just put a small weight of 200 grams on it. So it's a weight you found when insulation material is lying on a tape connection as well. And 3 days after I put it in the basement, I came down and wanted to make a picture, and the first 3 tapes already collapsed. But after 3 years, from 56 tapes, all different producers we could find, only 5 tapes were still resisting, and this was our solid glue. So it's important that you have a good how do you call it, a good initial tack, so it must stick fast and good to the surface, but it's as well important to have a high cohesion that it will last in the building for years. We have a very strong tack, initial tack. You see here the bonding after 1 hour, but if you wait a little bit longer, after 24 hours, it's getting even faster. Our glue is a little bit harder due to the fact we need a high cohesion, and it takes a little bit longer until it's penetrating in the surface, so it takes time before sticking. Durability is a question. We are working with adhesive tapes through clima since the middle of the 90s, so we have approximately 20 years experience with the tapes in the field. The glue we are using comes from the automotive sector. So in each car you found more than 40 square meters of tapes and glues somewhere put in the car. And they are working in cars with these glues for more than 35 years, so as well there it's proven that they have durability. But then we made an accelerate aging test. So they developed now in Germany a way how airtightness tapes have to be tested. And we said, okay, let's test our tapes for 50 years. And then we stick it to different surfaces, timber, Intello, Solitex membrane, they put it in the special climate chamber and they age it. And then after 50 years, after the aging time of 50 years, they took it out. They tested the adhesive strength and we found out, whoa, it's brilliant. So let's enlarge the agement to 100 years, and so we enlarged it to 100 years, and even after 100-year agement we passed this test. We couldn't enlarge it to 150 years because we have no samples left, and to test it for 100 years the testing time is 2 years, so it's very expensive and that's not so easy possible. Surface quality is a question, so when you have a nut good sticking, you can fortify the surface with a primer, so you bring the primer on it with a brush. You can stick the tape directly in this humid primer, it will dry later, and then you can achieve a very good bonding on difficult surfaces. And then it's a question, do I need the primer? If it's planed or not, if I have non-planed timber, do I have to use the primer? Then I say it depends who is sticking the tape to it. I can stick tapes to rough surfaces, but if you have maybe an installer who's not so well trained and he has no time, then the primer helps. Windows at the last point is simple to integrate because the windows are in the insulation layer or directly in the end of the CLT elements, and you can easily stick with the tape around it. And again, here it's up to you which quality you're choosing to achieve. So it's better to have this 3-ply tape then a streaming through this cracks is not possible, but it's always up to you what kind of a house are you planning and what airtightness quality you want to achieve. Yeah, last but not least, the solution with vapor retarder. And this is very interesting because now we try to bring everything in one element. It says, okay, let's the CLT be absolutely airtight and diffusion retarding, and to achieve this airtightness we have to buy these elements with the bonding on the narrow sides and with the high quality, so very high quality elements, and this may make the elements of course more expensive. So it's up to you when you plan a house, maybe to think about, okay, what's when I'm buying the CLT element which is not tested on airtightness but cheaper. And then I install from the outside a membrane, I have this water protection, I have a controlled airtightness layer. And this might be maybe the cheaper possibility, but it's up to you to calculate. So, last solution, airtight with vapor retarder on the outside. The advantage is the membrane itself is airtight. The building is completely wrapped, so this is easy for me to control. I can easily visibly control it, and I do not have to make my thoughts if I have very difficult detailings. So I do not have to think and control if it's really sealed with the tape airtight. So I just wrap it around and I have an easy airtightness. It can be easily connected to windows, doors and concrete. I have a visible control and it's an easy repair, and of course it is protected against rain. And I like the sheets you showed very well, where you have this moisture issues on your windows. So it offers a little bit advantages, especially if we go to the passive house sector. We want to build really, really airtight buildings, and then we avoid by wrapping it with the membrane this normal losses of maybe 1.2, 1.3 air changes per hour when we have to achieve a very good value of 0.6. Installation is easy, I don't have to say so much about it, just staple it to the surface, and then you can choose, because of the diffusion resistance of the element itself, you can work with a vapor retarder, this is what we recommend, or you can work with an airtight breathable membrane. Both are possible. After my opinion, a light vapor retarder offers more securities in these elements of windows, because there we have of course a gap of 1 or 2 centimeters. The effect is very low, but this is the better solution after my impression, but both is possible. We are working with a DA, it's a nice green membrane. It's airtight, watertight, watercolor more than 2.5 meters, so important to have this rain protection. It can be in the roof 3 months without any protection, in walls even longer. Nice for the installers, it's glare free, so white membrane would be nice, but not so good. And we have an NVTR value of 12 nanometers/gram, so it's a light vapor retarder. We have it available with the Connect version. So this means the tape is already on the membrane, and if you have these overlaps, then you remove 2 transfer layers and you stick glue and glue, and this is a very good airtight connection. But with the disadvantage that you as an architect cannot go around the building site later and see if everything is properly sealed. And so, yeah, think about it. I would prefer to seal it with the tape. This is faster, and if you have a good company you can rely on, you can trust, and this Connect version makes your life easier. The other way how to finish it was, I guess, well explained already by Rainer and all the speakers before me. This, of course, you can do with every solution, independent of you put something in between the elements, or you just do the tape solution, insulate it from the outside. We have very safe construction from the building physical point of view, so breathable on the outside or diffusion open. And this is why I cannot present you now with a hydrothermal calculation as well, because it's so easy from the building physical point of view. I hope you're not so disappointed you don't see the graphs and everything. It's so easy. With CLT you can build very fast and easy construction. Yeah, to bring it to an end, the airtightness of CLT must be reviewed critically, so it's changing over the time. We are not knowing how high the influence are in reality, but they will be there. Taping the element joints with the tape from the outside is more safe than putting something between the elements. The safest way is to put an additional airtightness membrane on the outside. It offers the maximum security regarding airtightness and weather protection. Good. So, and I hope that I gave you maybe some new ideas for your coming projects to think how can I realize that airtightness. It's up to you which quality you like to achieve. And all these three ways are possible, and yeah, I wish you all the best. So for me it was fun to be here. All the best for the coming projects, and yeah, we keep building damage free, or how do you say it as a goodbye? Be building damage free. Okay, thank you.